So the last video got interrupted due to a lack of storage space. 59 deleted videos later, we're ready to pick up where we left off. I was just pointing out that if we were to factor out a common factor from our third component here, we would wind up with a very delightful Pythagorean identity. So that's what I'm going to go ahead and do, assuming that I can get this all to fit. So let's copy this down one more time. We'll call this 4 times the sine squared of u cosine of v. 4 times the sine squared of u times the sine of v, and then factoring out that common factor, that would leave us with 4 times the sine of u times the cosine of u, and a Pythagorean identity, which will become 1. All right. So next up, we will need the magnitude of this cross product. Magnitude of the cross product of the partial derivatives. So we are going to take the square root of, oh yeah, you will need one that is that long. So 4 times the sine squared of u times the cosine of v. We're going to square that. We'll take 4 times the sine squared of u times the sine of v. We're going to square that. And finally, we'll take 4 times the sine of u times the cosine of u, and we will square that as well. So squaring appropriately, we are going to get, once again, big old square root, 16 sine to the 4th of u cosine squared of v, plus 16 sine to the 4th of u times the sine squared of v, plus 16 times the sine squared of u times the cosine squared of u. Now the very first thing that I'm going to do is notice that all three of these terms will have a 16 and a sine squared of u in common. I'm going to factor that out. So 16 times the sine squared of u is going to leave us with sine squared of u cosine squared of v plus sine squared of u sine squared of v plus cosine squared u. Now I'm going to use a pair of Pythagorean identities to turn what's left inside here into 1. I'm actually going to apply the square root to the 16 sine squared of u, call that 4 times the sine of u, and verify that everything left inside the parentheses will be 1. The first two terms have a sine squared of u in common, so I'm going to factor it out. When I factor it out, I'll be left with cosine squared v plus sine squared of v. A Pythagorean identity does in fact confirm that this is going to be equal to 1, leaving us with sine squared of u times 1 plus cosine squared of u. Then those two terms will in turn become 1 from another Pythagorean identity, leaving us with 4 times the sine of u. Now, one other thing that I'd like to do to make this process a little bit easier on us is, actually we'll do that when we're setting up the integral. The original surface integral that we had was the surface integral over the surface S of x squared x squared z plus y squared z ds. What I wanted to do is go ahead and factor out a common factor of z and call this x squared plus y squared times z times ds. In this form, we are ready to throw in the parameterization that we have for everything. So with that in mind, this will become the double integral over the domain D, which was the bounds that we came up with earlier on u and v. X squared plus y squared is going to become 2 times the sine of u times the cosine of v squared plus 2 times the sine of u times the sine of v squared. All of that is going to be multiplied by 2 times the cosine of u, that's our parameterization for z, times ds is now going to be equal to 4 times the sine of u dA. Now, through the use of squaring these and factoring out a common factor of, I believe, 4 times the sine squared of u, I believe we're going to get another Pythagorean identity in here. So this will be 4 times the sine squared of u times cosine squared v plus sine squared v times 2 times the cosine of u times 4 times the sine of u dA. Now with this guy being equal to 1, we are ready to go ahead and actually put some bounds in here for u and v. Bounds we had for v were from 0 to 2 pi, and the bounds that we had for u were from 0 to pi over 2. Again, those were in the last video. Looks like we're going to have a total of 3 sines of u. We're going to have a 4 times a 2 times a 4, so that'll be 32 sine cubed u times the cosine of u, du for the first bounds and dv for the second bounds. Now with those things in mind, looks like we can apply Fubini's shortcut here and break this into 2 single integrals. So this will be the definite integral from 0 to 2 pi for dv, and from 0 to pi over 2 for 32 sine cubed u cosine of u du. Now this one's going to require the use of substitution. Normally I would say u substitution, but delightfully ironic, we're already using u in here. If we let t be equal to the sine of u, then dt will be equal to the cosine of u du, which we have conveniently placed into the problem. The first integral is simply going to give us 2 pi, since that's what you get when you integrate 1. The other integral is going to be from lower bound of sine of 0 is 0, and sine of pi over 2 is going to be 1. This will become 32 times t cubed dt. So 2 pi sticks around. Integrating gives us 8 t to the 4th power, going from 0 to 1, which will give us 2 pi times 8 times 1 minus 0, for a final answer here of, hope you can still see this, 16 pi. Yeah, so that's your process of surface integrals over the course of 2 videos.